Okay, in this video I'm going to be talking about the Lagrange error bound for Taylor series. So basically you're going to approximate the value of a function using a Taylor series, and we will use the Lagrange error bound to set an upper bound for the amount of error in that approximation. And before we do the Lagrange error bound, we're going to need to go back and talk about the alternating series error bound. Okay, so remember we said that the error, which was, just kind of the size of the difference between the approximation and the true value, was no more than what? The size of what? Yeah, the next term. Yeah, just the next term. Okay, so that, for example, I'll just kind of remind y'all of how this worked. If I had some sort of infinite series, like, I don't know, the sum from 0 to infinity of -1 to the n over 2 to the n, and we used 3 terms to approximate s. Okay, so s3 equals, starting with 0, that's 1 minus 1/2 plus 1/4. So that's like 75 cents, I think. Yeah. And if we wanted to know the maximum possible difference between 3/4 and the true value to which this thing converges, now we actually can find this because it's a geometric series. Maybe I'll do that in a little bit. But, I'm just going to make that same diagram I made when we were talking about alternating series. Okay, so we started with 1 when we just took the first term. Then we go back to 0.5 when we subtracted a half, but then we're going to add a fourth. After that, we're going to add an eighth. Okay, but I know after I add that eighth, so that adding an eighth is going to go back about here. Oh, no. Okay, about like that. And I know that that's too far. So I know that the error in, approximating using the third sum is no more than the absolute value of the fourth term. Okay, well, the fourth term, since we started at 0, that's just going to be, okay. Yeah, the fourth term is A3. So that's always confusing when that happens. So what I'm going to do is I'm going to plug in 3, the absolute value of -1 over 2 to the third, which is 8, which is what we were expecting anyway. Okay, so the error is less than 1/8. Or maybe equal. Now, I'm going to actually kind of off to the side just say, well, this is a geometric series with first term 1 and common ratio -1/2. So that's the sum is 1 over 1 plus 1/2. Okay, so that's 3/2. 1 over 3/2 is 2/3. Okay, so the sum eventually converges on 2/3. Now it's a 3/4. If you subtract an eighth away from 3/4, you've gone past 2/3. Okay, that's how the alternating series error bound works. Okay, now for the Lagrange error bound. And since we are in Texas, I suppose it's okay to call it the Lagrange error bound. But I'll tell you, if you do call it the Lagrange error bound, you're opening yourself up to criticism from me and other people. And if y'all are about to go off to college in the north, I might not recommend calling it the Lagrange error bound, but that's just me. Okay, so it's the Taylor's theorem with Lagrange error bound. So I'm going to write the theorem up here. And pretty much what the theorem says is that the nth degree Taylor polynomial for a function plus the remainder is equal to the value of the function. And you might think, oh, that's really obvious. And the theorem is actually, a little deeper than that. But for our purposes, this is where we're at. That the approximator plus some sort of remainder is the exact value of the function. And then they actually give a value for this r. R is equal to the n plus first derivative over n plus 1 factorial times x minus c to the n plus 1. And what I forgot to say was that that's the n plus first derivative at some value of x. We'll just call it z, some special x. Now, the thing about this here Does this look familiar? What does this look like if we're using the nth degree Taylor polynomial? We've got the n plus first derivative, the n plus first factorial, and the n plus first power. It just looks like the next one. Okay? This is just the next term. Okay? And some other time, I'll come back and show you how this is actually the mean value theorem for n equals 0. Okay? Where there is a value of the derivative where the average rate of change equals the instantaneous rate of change. That's something that we can show using this. Okay? But this is not really what we're going to use for the error bound, right? I don't have anything saying that the error is bounded from above by this quantity. So the corollary is that the error is less than or equal to the maximum possible value of the next term. Or the maximum possible value of the absolute value of the next term. So, and I'm going to say with, no loss of generality, for x being between the centering point and the point that we're interested in using for our approximation of n plus first derivative of f, n plus 1 factorial, x minus c to the n plus 1. All right. Really what we're thinking is maximum possible value of the next term. That's the Lagrange error bound. The first example I've got, this is some kind of old multiple choice question. I didn't write out the whole statement of the question, but I'll read it to you. The function f has derivatives of all orders for all real numbers, and f's fourth derivative is e to the sine x. If the third degree Maclaurin series for f is used to approximate f on the interval 0 to 1, the closed interval 0 to 1, what is the Lagrange error bound for the maximum error on the closed interval 0 to 1? Okay. So we're going to find the Lagrange error bound when we're using the third degree Maclaurin polynomial. Okay. So if we're using the third degree Maclaurin polynomial, then we know that the error will be less than the maximum possible value of the fourth term. Okay, so that'll be maximum possible value of the fourth term. Well, I know what the fourth term is. It's the maximum possible, well, I guess I need to write maximum possible value. Maximum possible value on x between 0 and 1 of, well, f's fourth derivative. I was trying to think if I wanted to actually substitute on that, but I don't. Not yet. 4 factorial times x to the fourth, because it's a Maclaurin series, centered at 0. All right. So if you think on the interval 0 to 1, when is e to the sine x going to be largest? Well, this is oftentimes a calculator question, and it looks like on this multiple choice they were assuming you had a calculator. Okay. So one thing you could do is kind of just graph e to the sine x and see where it's maximal. Okay. Another thing you could do, I'd expect that the answer to this question is actually finding the maximum possible value of e to the sine x. But you could also say that an error bound for this, it wouldn't be as good of an error bound, well, by just taking sine x and saying, well, that's always less than or equal to 1, so the fourth derivative is definitely less than or equal to e. Okay. So I could do that and say e divided by 4 factorial times, well, the maximum possible value of x to the fourth on 0 to 1 is going to be 1 to the fourth. Okay. That would be, okay, e divided by 4 factorial. I don't even know what that is. I can find my calculator. Here's one. Okay, so I've got e to the 1 divided by, divided by 4, divided by 3, divided by 2, 0.113, which is an answer choice. Okay, maybe that's a good answer choice. Maybe that's not the best answer choice. Okay, so let's actually look at the graph of e to the sine x. All right, so here I am. I'm entering e to the sine x. I'm going to graph this thing on the window 0 to 1. And I know that the maximum possible value of this in the y direction is e to the 1. So I'm going to actually just type that in there. Okay, and then I'm going to do it. There we go. The maximum value happens at e to the sine of 1. Okay, so I might even just calculate the value of this function at x equals 1. And it'll say 2.3197. 231.97. So, that's something else. 231.97 divided by 4 factorial. Okay, right? We need to use division bar to throw all of these numbers down in the denominator if we're not going to use a parenthesis. And that's 0.097, which is also an answer choice. So this is really the Lagrange error bound. If you're allowed a calculator, you should probably use it to get the best error bound you can. Okay, if this was a non-calculated question, then the, e over 4 factorial likely would have been best. So what I'm going to say is that the maximum possible value of f's fourth derivative is e to the sine 1 divided by 4 factorial, okay, which is that 0.097. All right, and then the next example I've got for you, and there is one in your free response packet that's got a table of values that I really like as a Lagrange error bound question, but I think that might be on the homework. Okay, the homework for tonight is just to do the quiz that's going to be on the calendar. Okay, it's the Lagrange error bound quiz. You should just do that. That'll be the best way to prepare for the couple of questions you get on that on the test. And if you guys still got more stuff, come see me tomorrow, and I'll have plenty of answers for you. Okay, so let P4 be the fourth degree Taylor polynomial for f about x equals 0. And just so everyone that's watching at home knows, this is from the 2011 Cal BC exam. So you can go and look up the question and the solution, if this is not doing it for you. Okay, so P4 is the fourth degree Taylor polynomial for f around x equals 0. Using information from the graph of f's fifth derivative shown above, show that the maximum possible difference between the fourth degree approximation for f of 1/4 and the true value of f of 1/4 is 1 over 3,000. All right, so what I'm going to say is that this that I'm highlighting in yellow is code for the error. Okay. I'll just write that there. But I know that error in the Lagrange error bound case, okay, so they're showing you the absolute value of the next derivative. That's code for Lagrange. Also, if you go back and look through the free response packet, you'll see lots of this is an alternating series with terms that decrease towards 0 in absolute value, or something like that. And, that's kind of a hint that you want to use the alternating series error bound. So, experience with that is going to be the best for y'all. All right, and so the error is less than the maximum possible value of the next term. Well, the next term is going to be that fifth derivative, f's fifth derivative of x divided by 5 factorial times x to the fifth. And we're going to make that, between the centering point and the point that we're interested in approximating, 0 to 1/4, for our possible x values. Okay, so this is the maximum of f's fifth derivative between 0 and 1/4. What would be a good error bound on this graph? Y'all probably can't see it that well. Okay, but if you go up to here, this is the maximum possible value. That is certainly less than 40. So 40 will kind of be the maximum possible value of the next derivative. And, okay, so x to the fifth is 1/4 to the fifth. That's a maximum possible value of x to the fifth. And this is something that we're going to show is less than 1 over 3,000. All right, so we've got 40 over 5 factorial, that's 5, 4, 3, and 2, and 5 powers of 4 in the denominator. Okay, and so what I'm going to do is I'm going to take this 40, and I'm going to turn it into a 5 times 4 times 2, right? That's what 40 is, 8 times 5. And I'm going to start to cancel stuff off. I've got the 5s, I've got the 4s, I've got the 2s, and then I've got basically 5 powers of 4 makes 256. And I've got a 4 powers of 4 is 256. Times 4 times 3 is clearly less than 1 over 3,000. Okay. Keep working Lagrange error bound examples. They get easier. The big thing is the form of the error bound, that maximum possible value of the next term.